Similar to two population means, we can also compare two populations proportions. To do that, we need to know three properties of the sampling distribution of the difference between two samples proportions. So similar to the case of the sampling distribution of the difference between two sample means, the mean of the sampling distribution of two samples proportion is equal to the difference between two populations proportions. So in other words, we can say that the difference between two samples proportion is an unbiased estimator of the difference between two populations proportions. The standard deviation of the sampling distribution for the difference between two samples proportion is calculated in the following way. So we take the square root out of proportion from population 1 multiplied by Q1 divided by the sample size of the first population, of the first sample, plus proportion 2 from the second population multiplied by Q2 divided by N2, the sample size of the second sample. And if the sample sizes are large, we can, so in other words, when we multiply N by P and it's higher than 15, or when we multiply Q by N, it's higher than 15, then we can say that the sampling distribution of the difference between two sample proportions is approximately normal. So to construct a confidence interval for the difference between two population proportions, we have two cases. The first case is when we know P1 and P2, so the population proportions, and the second case is when we don't know them. So when we know them, we take the difference between two samples proportion and plus minus the critical z-score at the level of significance alpha over 2 multiplied by the square root out of the standard deviation of the sampling distribution that we had here. But as we already know, we almost never know the true population's proportions, therefore we have to approximate them. So if you look at this formula, you will see that the first part is the same, so the difference between two samples proportion plus minus the critical z-score at the level of significance alpha over 2 multiplied by the square root out of, and here we have P with the hat multiplied by Q with the hat, and to get P with the hat, we can do the following. So we sum x1 and x2, so the number of successes in sample 1 and sample 2 divided by the sample size 1 plus the sample size 2. Or we can also take the sample size 1 multiplied by the proportion from the first sample plus the sample size 2 multiplied by the proportion from the second sample and divided by the sum of the two sample sizes. So this P with the hat, this is nothing else but just the weighted sum of two proportions. And Q is always calculated as 1 minus P. And after this, we multiply this product by 1 over N1, so the sample size 1 plus 1 over N2, sample size 2. And once again, let's revise what those values are. So P1 with the hat and P2 with the hat, those are two samples proportions. If they don't have hats, they are population proportions. X1 and X2, this is the number of successes in two samples, and 1 and 2, there's two sample sizes. And Z alpha over 2, this is the critical Z value at the level of significance alpha over 2, and alpha, this is just the significance level specified a priori. We can also do hypothesis testing for the difference between two population proportions, and we have two cases when we know the population proportions and when we don't know them. So when we know them, the z-score will be equal to the difference between two samples proportions divided by, as we already know, as the sampling distribution of the difference between two samples proportions. But the more realistic case is when we do not know the true population proportions, and in this case In the denominator, we would have p with the hat multiplied by q with the hat, which we know from the previous step how to calculate. Here is the formula. And the brackets, and in the brackets we have 1 divided by n1 plus 1 divided by n2. And here is the summary of hypothesis testing procedure for the difference between two population proportions. So the null hypothesis for all the three tests is the same, is that the difference between the population proportion 1 and population proportion 2 is 0. So in other words, those population proportions are the same. And the alternative hypothesis in case of the negative tail test is that this difference is negative. The positive tail test assumes that the difference is positive, and as for the two-tailed test, the difference is not equal to 0. And similar to the case of 2 means, the rejection rule for the negative tail test is when the estimated z-score is lower than the negative value of the critical z-score at the level of significance alpha. In case of the positive tail test, the rejection rule is when the estimated z-score is higher than the critical z-score at the level of significance alpha. And as for the two-tailed test, the null hypothesis is rejected when the estimated z-score in the absolute terms is higher than the critical z-score at the level of significance alpha divided by 2.